Okay, for this problem, we're going to apply our study of differential equations to this problem in physics involving a spring. Our governing differential equation for the motion of a spring is mu double prime plus gamma u prime plus k times u equals 0, where m is the mass of the spring, gamma is the damping constant, and k is the spring constant. Okay, so first things first, the damping constant is actually given, so 10 pounds-seconds per feet. Now this is a very unusual unit. The reason it's unusual is because u prime is measured in feet per second. So if I have seconds per feet times feet per second, this part cancels and I'm left with just pounds. Okay, so let's see what we have for the spring constant. It says here that a mass weighing 20 pounds stretches a spring 6 inches. So using Hooke's law, force is equal to k times x. The force is equal to 20 pounds. Pounds is a unit of force, not mass. 20 pounds is equal to k times x. X is in inches, and so we'll use that as a half of a foot. And so therefore k is equal to 40 pounds per foot. It takes 40 pounds of force to stretch it a foot. It takes 20 pounds of force to stretch it half a foot. Now u is measured in feet, and so if I take k times u, that's going to be in pounds again because that'll cancel the denominator of this unit. Okay, next we have to get to the mass. The mass of the spring is determined by force is equal to mass times acceleration, where the acceleration is this time the acceleration due to gravity. The force is 20 pounds. That's the force of the Earth pulling on the mass, times the acceleration due to gravity is 32 feet per second squared. Now it's not exactly 32, but we'll use 32 for the purposes of this course. So that means that m is equal to 5/8 times pounds per second squared over feet. Now this is a very unusual unit. In the English system, this is actually called a slug, if I remember right. But we're not going to worry about slugs. We'll just write 5/8 pounds per times second squared over feet. And so when I multiply by acceleration, feet per second squares cancel, and I'm left again with just pounds. Okay, so practical effect is that we have 5/8 u double prime plus 10 u prime plus 40 times u is equal to 0, using the k and the m that we just found. Let's clear out the denominator. We get 5u double prime plus 80u prime plus 320u equals 0. And I can do a little bit better. If I divide by 5, I get u double prime plus 16u prime plus 64u equals 0. So that is my governing differential equation. I also have initial conditions. If it's pulled an additional 3 inches, so u of 0 is equal to 1/4 of an inch, pulling it from equilibrium. So u of 0 is equal to 1/4. And also it's pulled and released, so there's no initial velocity that's given, so u prime of 0 is equal to 0. So that is the setup for how I read this problem and then set up the governing initial value problem. Now, everything else from this point forward is going to be like the other problems in this review, where I have to solve this second-order differential equation. So the part of the problem that's new is how do I take this word problem and translate it into a differential equation. Okay, so now that we have this, we can start solving. We set up the characteristic equation r squared plus 16r plus 64 equals 0, which factors as r plus 8 squared equals 0. So r equals -8 is a double root of the characteristic equation. And so that means that y of t is equal to c1 e to the -8t plus c2 times t e to the -8t. In the lingo of springs, this is an example of something that is critically damped, meaning that I had a double root here. And I should have wrote u instead of y, I apologize. Okay, so now I use the initial conditions, u of 0 and u prime of 0. So let's get the derivative. I get negative 8c1 e to the minus 8at plus derivative of the first times the second plus the first times the derivative of the second. Okay, now we plug in 0. We get that u of 0 is equal to c1 plus 0. U prime of 0 is going to be equal to negative 8c1 plus c2 plus 0. And this is given to be equal to 1/4, and this is given to be equal to 0. So c1 is equal to 0. C1 is equal to 1/4. And we have that 0 is equal to negative 1/2 plus c2, so that c2 is equal to 1/2. And so therefore I conclude that u of t is going to be equal to 1/4 e to the negative 8t plus 2t times e to the negative 8t, plugging in the constants for c1 and for c2. And if you wish to factor this, that's fine. And that is the equation of motion for the spring.